Okay, here we are again. Lab we're going to do this week, actually starting next week, depending on when you watch the video, is going to be another kinetics. This time we're going to do kinetics using the pseudo rate orders, or what's called the integrated rate laws, graphical rate things. I told you last time there's two different methods. There's a method of initial rates, which we did last lab, and then we're going to do the graphical rates this time. So when we did the method of initial rates, you remember the whole thing was we wanted to make sure that none of the concentration of the reagents changed during the course of the reaction. That's why it's the initial rates. And then we do two different reactions where the concentration of one of the reagents changes. Well, with graphical rate laws, graphical rate values, we actually want the concentration of one of the reagents to change during the course of the reaction. And we're going to look at how the rate of the reaction changes with a change in concentration of the reagent. And based on how the rate changes with a change in concentration, that's going to tell us what order with respect to that reagent is. And remember, this comes from the rate limiting step. That is the coefficients from the rate limiting step that we don't know. We have to figure that out by experiment. So in this one, you're not going to get fractions. You're not going to get any decimal places. It's either zeroth, first, or second order. That's it. We'll talk about doing the lab in just a little bit and some of the problems you may encounter or some things that you may need to pay attention to. Right now, let's go through and make sure we understand the concepts, because there's not a lot of math in this. There's just concepts that need to be understood. So let's do a zeroth order. Right? In zeroth order, what does that mean? Well, that means the concentration of our reagent is raised to zero. Zero raised to anything, if that equals the rate, proportional to the rate. Well, zero raised to anything is 1. That means when A goes to 2 times A, it's still 1. A goes to 4 times A, it's still 1. 1/2 A, still 1. 1/10 A, still 1. Rate does not change based on the concentration of A. The rate is independent of the concentration of A. Now, that doesn't mean that A is not part of the reaction. It just means that A is not part of the rate limiting step. So if we plotted out the concentration of A over time, what would we see? Well, we're not going to get a straight line like that. We're going to get a straight line like this. Why? Because even though A is not involved in the rate, it still is being consumed during the reaction. So its concentration continuously goes down. It's just as its concentration goes down, it doesn't change the rate of the reaction. The rate of the reaction remains constant, but it still is going down during the course of the reaction. So we plot out concentration versus time. We're going to get something like this, where the slope is the negative K. For what we're going to do, it's going to be pseudo K, because we're not going to consider the OxyClean concentration in there, but that's okay. For what we're doing, it's not going to make any. It's not going to make any difference. It's not going to have any effect on it. Okay, so that's zeroth order. When it's zeroth order, we plot out concentration versus time. We get a straight linear line with a negative slope. The negative slope is equal to the negative of K. K's are always positive. How about first order? Okay, with first order, it's like raising A to the power of 1 equals the rate. Well then, what happens? If we double the concentration of A, the rate goes twice as fast. If we half the concentration of A, the rate goes half as fast. We do a quarter of A, it's a quarter as fast. As A decreases in concentration, the rate slows down. So what happens? If we plotted out the concentration of A versus time, it starts off degrading fast because A's concentration is high, but then the concentration of A goes down and the rate at which it decays slows down, and therefore we get this exponential curve. Well, if we want this exponential curve to be linear, and we do because the statistics and everything else of linear equations are much, much better to deal with, then we take the natural log and change the exponential decay into a linear line, and that has a value of negative K. Okay, so we take our data, we plot it out with concentration versus time, we get this weird slope. Then we plot it out for Ln, the concentration of A versus time, and we should get a linear slope if it's first order. If it's zeroth order, this won't look right. This will look right. If it's first order, that won't look like. It'll be like a exponential curve, and this will be the correct one. How about second order? Okay, with second order, that's like raising a to the second power. As the concentration of A doubles, the rate goes up by 4. Concentration of A goes to 1/3, rate goes down by 9, 1/9. It goes by the square of the concentration of A. So again, if we take this and we plot out the concentration of A versus time, what's it going to look like? Now it really starts dropping fast, but as A decreases, it really changed very, very fast, and we get this weird scooped-looking plot. So what do? If we plot 1 over A's concentration, then what happens? Well, then as this goes to 1/2, the plot goes to 2. As this goes to 1/8, it goes to 8, right? Because 1 over 1/8 is 8. As this goes to 1/16, this goes to 16. So what we do is we get a positive linear slope that is equal to K. All right? So that's how we do it. We run the reaction. We take our data. We don't know what the order is, but we plot it out with concentration versus time. Then we plot it out ln concentration versus time. Then we make another plot with 1 over concentration versus time. And we look at the plots. Whichever one has the best linear fit, that's the order with respect to that reagent. All right, and we can determine linearity by using an R-squared value that we get when you make your chart, when you make your graphs. Make them with the trend line equation, because we need the equation to get K, and also with the R-squared value. Now, R-squared is not the coefficient of correlation coefficient, which is properly called the Pearson product moment correlation coefficient. I know you don't need to know that, but you never know what you need to know. R-squared is the coefficient of determination, but it's even better for what we're trying to determine. It actually gives us the proportion of the variation in the data that is covered by the model. More than you need to know, but I wanted to mention it so we're thorough and everybody understands. R-squared, not a correlation coefficient. It's something different, but it's even more useful for what we're doing. So, like I said, not a lot of math in this. You just have to make the plots. Now, don't plot all these on top of each other. Make 3 separate graphs. You can put all graphs on the same piece of paper, but make 3 separate graphs, one with the concentration, one ln of concentration, one over the concentration. Put in the trend line value and put in the R-squared value. Whichever one has the best R-squared value, that will be the order with respect to that reagent, which is the blue dye for the lab that we're doing. Okay? Is that clear? Now, one other thing we're going to do is we're going to figure out the activation energy. Okay, so for activation energy, let's see, let me get a new piece of paper here. For activation energy, this was discovered a long time ago. Arrhenius and a few others came up with this. But basically, the K is equal to E times the negative of the activation energy over R. Okay, R is a gas constant. There's a ton of gas constants, but this case we're talking about energy. So the gas constant we're going to be using is going to be, the gas constant has a value of 8 point, what is it? Let me make sure I get this right. Don't say something silly. 8.3145 joules per mole Kelvin. Kelvin. Why do we have to use Kelvin? Got to use Kelvin because Kelvin is the only direct measure of energy. Okay, when you go from 50 Kelvin to 100 Kelvin, the energy of the system has doubled. When you go from 50 Celsius to 100 Celsius, the energy has not doubled. So almost everything that's done in science goes by Kelvin, and that's because Kelvin is the true measure of the energy of a system, and we're talking about energy here. So we have to use Kelvin. So what we want to do is we want to figure out what is the energy of activation for this system that we have. So for our benefit, and let me just see, make sure I got everything doing things right here. Oh, sorry, it's R over RT. I forgot to put the T in there because I'm going to pull it out in just a second. So what do we want to do? Well, we just saw this is an exponent. This is going to give us an exponential curve. We don't want that. So we're going to take ln of both sides. ln of k, and sorry, it's lowercase k, is going to be equal to what? Well, we take ln of e to the negative. That's going to be equal to the negative EA over RT, just like that. We can pull this temperature out, and we end up with ln of k equals negative EA over top of R times 1 over T. Now we want to find out the change in energy based on a change in the activation. The activation energy, we want to get a change in activation energy based on our Ks. So what we do is we run the reaction at two different temperatures. Then we're going to take final minus initial. So that's ln of K final minus ln of K initial, and that's going to be equal to negative EA over R times 1 over T final minus 1 over T initial. Well, if you know your rule of logs, the negative of a log is the same as 1 over the log, so I can change this to say it's ln of K final over K initial is equal to negative EA over R times 1 over T final minus 1 over T initial. Even worse than that, if you go online and you look around, you're going to find some people that take the negative sign off of here and then flip the final and initial here. Gives you the same value, but you got to be careful for what you're doing. Thermodynamics always drives people crazy because you gotta pay attention to the sign on everything. So make sure if you've got final over initial, it has to be final minus initial here. That will give you the negative EA over R. You don't get a direct calculation of that. Let's do an example and see. So the example is in your handout. We have a second order reaction observed. Doesn't matter what the order is. The rate constant at 3 degrees Celsius was found to be 8.90 times 10 to the negative 3 liters per mole. And then at 35 degrees Celsius, it was found to be 7.10 times 10 to the minus 2 liters per mole. Okay, so first thing is we're using R, and the R we're using is the 8.3145 joules per mole Kelvin. Since it has units of Kelvin, we have to have our temperature in Kelvin. So how do you get Kelvin? You add 273.15. Remember, this is an addition, so these sig figs are right. So 3 plus 273.15 Kelvin equals 276.15 Kelvin. 35 plus 273.15 Kelvin is what? It's going to give us 308.15 Kelvin. So those are our two temperature values. All right. Now we can set up our equation, and we can say it's ln K, that's lowercase k, final over K initial. It's lowercase k because you see when we get into equilibrium, we'll use capital K's. Different thing. It's going to be equal to negative EA over R times 1 over, what's our final? Well, you can really choose what you want to be final or initial, as long as your final and initial here is the same as your final and initial here for temperatures. I'll use the 308.15 Kelvin as a final, and that's minus 1 over our initial, which was the 273.15 Kelvin. Okay, that means my K here for the initial final is going to be the 7.10 times 10 to the negative 2, and my initial is going to be the 8.90 times 10 to the minus 3. So let's solve the temperature. Let's solve ln of the two rates of reaction first, and then we can solve for EA over R. So ln of the two different things here should give us a value of 2.077. And that's going to be equal to negative EA over R times, and our two temperatures, one over top of the other, is going to give us a negative 3.7604 per Kelvin. This is unitless because we had the units of liters per mole, one over the other. It cancels out, so we get a unitless value there. Now let's figure out the value for this. Well, that's the 2.07 divided by negative 3.76047 per Kelvin. And if we work that out, what do we get? Just flip over to the next page. I'm going to get negative 5.523 times 10 to the 3 Kelvin. Remember, it's 1 over Kelvin, the Kelvin comes up. This is the value for negative EA over R. So if we want to get the activation energy, EA, we have to take this value times negative R. Okay, so negative 8.3145 joules per mole Kelvin times my negative 5.523 times 10 to the 3 Kelvin. Kelvin cancels out. I end up with units of joules per mole, exactly what I wanted, energy, and I end up with 4.592 times 10 to the 4 joules per mole. So that's the way you figure out the activation energy. You do the experiment, two different temperatures. You get the Ks for those two different temperatures, and then you do this plot and you do this calculation to figure out the activation energy. Okay, actually running the experiment. What do we do? So I ran it this morning a couple of times, and I got good results. Works very, very well. But one of the problems is that to get all of the OxyClean to dissolve, you have to be very careful. It takes a while. You have to slowly stir it, let it sit, slowly stir it, add in a little bit more, and keep doing that. It's going to get cloudy with little tiny bubbles, and it's going to get foamy on top, and the foam is the biggest problem to deal with. So be careful, take your time. It literally takes like a half an hour to get it all dissolved well. But always lift the beaker up. Remember, the beaker's kind of opaque, so we don't want to do the reaction in that. We want to do the solution preparation in that. Lift the beaker up under a light and look and make sure there's no solid on the bottom of it. Once all the solid has dissolved, then you can proceed with the rest of the reaction. Get your water out, 80 mils of tap water or DI. I don't think it makes a difference. It didn't for me. And then try and measure out 20 mils of that OxyClean solution. Now, again, it's going to have a lot of foam on top. So try and take your spoon when you're pouring it and hold back the foam so that you don't get a lot of the foam into the graduated cylinder. Measure out the 20 milliliters. But be careful. Try and keep it as close to 20 milliliters as you can with as minimum amount of foam. If a little foam gets in there, don't worry about it. When you pour that into your cup, the cloudiness will disappear. It'll clear up. Stir it very slowly and gently, and try to get all the foam out. If there's a lot of foam, try and take the spoon, kind of move it over to the edges, maybe pick the foam up and put it back in the beaker. Get that foam as much out as you can, because if that covers the top, you won't be able to get good readings. Once that's all dissolved, then set that cup on top of the red paper and take your foam with the app and situate it. Find out what way is situated best. It's a shame that the cameras always have to be on the end of the phone, because then you have to kind of hold it on the cup. And get it to where you right in the middle of the cup and zoom in and until you have a nice tight picture down there. And then hit the reading a couple of times and make sure you're getting fairly consistent readings. Do that 3 or 4 times for the initial reading. That's your blank. Then take your dye and just put 1 drop, stir it. You got 15, 20 seconds. You're not going to take a reading till 1 minute. I just used a clock on the wall and watched the second hand go around. It doesn't have to be to the 10th of a second. It just has to be pretty close. I put the phone back on there and I let it go around till it was 1 minute, and then I took a reading. And then I just sat there and waited. After 30 seconds, took another reading and recorded it down. Took another reading, recorded it down. And I did that for the full 8 minutes. I didn't have any problem. There was no foam around that caused any interference. I did get quite a bit of variation, unfortunately, near the end. You'd think you'd get more in the beginning, but as the red got stronger that I was reading, I actually got a couple readings that were kind of weird. And once or twice, I had to take my phone and readjust it to make sure I was in the right position, take another reading, and then the reading went up, because the reading should constantly go up by a small, at least some amount. And so I got good readings, plotted it out, and I got good results. So hopefully same thing will happen for you. You're going to be making up 100 mils, but you're going to do the temperature, the lower temperature twice, and you're going to do the upper temperature twice. So that's going to take 80 mils. When you do the higher temperature, you've got your water that's warmed up, not boiling, but, pretty warm. Make up your solution for your OxyClean and just take the cup and kind of gently move it back and forth in the solution until it warms up. Have the thermometer in there in the cup of the OxyClean solution until it warms up to at least 10 degrees above what it was for the other trial. And then when you get it to 10 or 12 degrees above that, record the temperature, add your 1 drop, and proceed as normal. Do that twice. The temperature has to be the same for those 2 runs, okay? It has to be the same. So make sure it's within 1 degree or less of what it is. It should be less than 1 degree before you do it. Then when you've got all your data, just take the average of those 2 runs and then use that to calculate out the absorbance. How do you get the absorbance? Absorbance is equal to the log of the blank over top of the actual measurements you got. You'll see it different ways, negative log of the measurement over the blank, whatever. They all work out. Just do that simple calculation. I just did it in an Excel sheet. Plot that out. Take ln of the absorbance, plot that out. We can use absorbance. Yeah, I need to talk about that, I guess. We can use absorbance for concentration because Beer's law says that absorbance is equal to a proportionality constant times the path length times the concentration. Since these are both constants, you're not changing the depth of the solution, and you're not changing the extinction coefficient, or molar absorptivity, they call it nowadays. So these are directly proportional, so we can measure absorbance and replace that for concentration, and it works exactly the same. Okay, so do that. You should get good results. Just take your results, make sure you do your calculations, answer the questions in there. You're going to do it elevated, then you're going to do the calculation for the activation energy. And then make sure you turn in your 4 graphs, right? You're going to have 4 graphs. 3 with the initial room temperature plot that you do to find out what the order with respect is. Once you know what the order with respect to whatever it is, let's say it's zeroth order. Okay, once you know it's zeroth order, then for the elevated temperature one, you just do a zeroth order plot. You don't have to do all 3 plots again. We know what the order is. Just do 1 zeroth order plot, get your K value from that, and those are the Ks that you use to do the activation energy. So there should be 4 plots. You can do all 4 plots on 1 piece of paper. Probably be better to do 2 plots on each piece of paper that you upload. Take a picture of them or whatever, simply because you want to be able to see the R squared, and I want to be able to see the trend line values. So make sure you upload a picture of those 4 graphs that you made and your data sheets. It's a lot this time, but it's going to be like that sometimes. And then we'll meet again next week for another lab. Otherwise, have a good one.